Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about diagonalization. There are certain applications where it's easier to work on a particular problem if you can work instead with a similar matrix D, where D is a diagonal matrix. It has perhaps non-zero entries on the diagonal, but everything else must be zero. We may run through an example later on. If there is an invertible matrix P, where A is similar to, through the matrix P, some diagonal matrix D, then the matrix is called diagonalizable. I want you to say that out loud. Diagonalizable. The matrix A, which is square, is called diagonalizable if there exists an invertible matrix P and diagonal matrix D such that A is P inverse D P. In other words, A is similar to a diagonal matrix. A quick note on some simplified computations. If I have a matrix D1, 0, 0, D2, then D squared is calculated very simply. You just square the diagonal elements. So if D is of the form D1 through Dn, zeros everywhere else, then D to the power of K is just the diagonals raised to that. Is just the diagonals raised to that power, and zeros everywhere else. How do I calculate e to the power of a matrix A? It is, by definition, that means because I said so, the identity plus A plus 1 over 2 factorial A squared plus 1 over 3 factorial A cubed, and so on forever. We're using the Maclaurin series, but we're substituting the matrix A in instead of X. 1 has to take the form of the identity matrix. So if A is a diagonal matrix, all of these computations are easy to find. E to the power of a diagonal matrix is I plus D plus 1 over 2 factorial D squared, and so on. This will give you 1 plus D1 plus 1 over 2 factorial D1 squared, and so on. 1 plus D2 plus 1 over 2 factorial D2 squared, and so on. Down the diagonals, zeros everywhere else. This gives you e to the D1 through e to the Dn, zeros everywhere, by the usual Maclaurin series. If the matrix A is not diagonal, exponentiating the matrix becomes a lot harder, unless the matrix is diagonalizable. Let's let A be P inverse D P. Let's calculate e to the power of A. By definition, it's I plus P inverse D P plus 1 over 2 factorial P inverse dP squared, and so on. I want you to think about this P inverse dP squared. That means 2 factors of P inverse dP. But we can regroup this so that these middle factors cancel out and just become the identity matrix, which then goes away. We get P inverse d squared P. So if I have P inverse dP to the power k, that always simplifies as P inverse d to the power k P. So for sake of argument, consider the identity matrix to be P inverse I P. The next term is P inverse d P, 1 over 2 factorial P inverse d squared P, and so on down the line. On the left, on every single term, we have a P inverse. It can be factored out. You can factor out the P on the right, which gives us P inverse e to the d, which we know how to calculate because d is diagonal, times P. So if a matrix A is diagonalizable, then finding its exponential isn't so bad. You just have to know this matrix P. If I have a differential equation of the form dx dt is a times x, where x is a vector, this then will represent a linear system of ordinary differential equations. Let's suppose that x evaluated at 0 is some number, some vector x naught. Then it can be shown that the solution to this system is x of t equals e to the at times x naught. The problem is, how do you calculate e to the at? Now, if a is diagonalizable, e to the at isn't so hard to figure out. That's going to be P inverse e to the d t times P times the vector x naught. We see that if the matrix A is diagonalizable, we can solve all linear homogeneous systems of ordinary differential equations by exponentiating a matrix. Not a bad idea, but in our differential equations class, we teach you another method for constructing solutions using eigenvalues and eigenvectors that is highly efficient. Nonetheless, there are so many applications for diagonalization that we need to teach you how to do this in general. We have the following theorem. A matrix A that is square is diagonalizable if and only if. That means we're going to give a complete characterization of when a matrix is diagonalizable. It has a basis v1 through vn for Rn consisting of eigenvectors. So only if the matrix A generates what is called an eigenbasis is this matrix diagonalizable. Not every matrix is diagonalizable, as I'll show you. But first, we need to prove this theorem. This is an if and only if proof, so we need to prove this in both directions. So let's suppose A generates an eigenbasis v1 through vn for the vector space Rn. We'll set P inverse to be the matrix with columns equal to these eigenvectors in our eigenbasis. I want you to look at A P inverse. That will be AV1 through AVN. But because these are eigenvectors, we'll have lambda 1 V1 through lambda n Vn. We can write this as follows. We can write it as V1 through Vn times the diagonal matrix lambda 1 through lambda n. When you multiply here, the first vector gets multiplied onto the lambda 1, and so on down the line. The last vector multiplying onto that lambda n. And so we get P inverse times the diagonal matrix. The diagonal matrix consists of eigenvalues. We have AP inverse equals P inverse D. Multiplying both sides on the right by P gives us A is P inverse D P. And that completes the proof in this direction. In the other direction, suppose the matrix A is diagonalizable. We'll set V1 through Vn to be the columns of P inverse in light of our proof in the other direction. So that P inverse is V1 through Vn. Since the determinant of P inverse is not 0, because P inverse is invertible, its inverse is P, this set, V1 through Vn, is linearly independent. And since it has n elements, and they lie in Rn, that implies it's a basis for Rn. We need only show that these are, in fact, eigenvectors. To that end, we'll look at AP inverse, which we know is equal to P inverse times D. Multiply both sides of this equation by P inverse on the right. Notice that what you get is AV1 through AVN. And on this side, you get what you get depends upon what D is. Let's suppose D has the form lambda 1 through lambda n, not yet assuming that these lambdas are in fact eigenvalues. But when you do the multiplication, you'll get lambda 1 V1 through lambda n Vn. Now, by equality of the columns in these two matrices, we get A Vk is lambda k Vk, and that implies we have now an eigenbasis. And so that's the end of the proof. As an example, let's look at the matrix A, which is 0, negative 2, 3, 5. We want to diagonalize this. To diagonalize it means we're going to find a matrix P that is invertible and a diagonal matrix D with eigenvalues on the diagonal, where P inverse has two columns, each of which consists of an eigenvector from this matrix A. So to solve this problem, we need to find eigenvalues and eigenvectors first. So step 1, let's set 0 equal to the determinant of A minus lambda I. So we'll subtract lambda from the diagonal elements. We'll have negative lambda times 5 minus lambda, and then we subtract a negative 6. So that'll give us a positive lambda squared minus 5 lambda, and then plus 6. And we know how that factors. Lambda minus 2, lambda minus 3. We get eigenvalues of 2 and 3. Therefore, our matrix D is 2, 0, 0, 3. We need to find the eigenvectors now. That's our step 2. We do those for each eigenvalue. Subtract 2 from the diagonal elements and put it next to 0, 0. As you can see, we'll get our eigenvector v1 to be 1, negative 1. Switch and negate. You can rescale. We can cross this one out because we can row reduce to have a row of zeros. Multiply through by negative 1/2 if you wish. You'll get 1, 1. If you switch to the negate, 1, negative 1 will do. For lambda equals 3, we subtract 3 from the diagonal. We can cross out one of those two rows. Looks like our v2 will be the vector 2, negative 3. We can choose P inverse then to be the matrix 1, negative 1, that corresponds to 2, and then 2, negative 3. P is the inverse of this matrix. The determinant is negative 3 minus negative 2, that gives us negative 1. 1 over the determinant, switch the diagonals, negate the off diagonals. Multiplying by negative 1, we'll have 3, 2, minus 1, minus 1 for P. We have B, we have P inverse, we have D. A will be P inverse dP. We should check this since this is our first time diagonalizing a matrix. Let's write this down. We'll have 1, 2, negative 1, negative 3, 2, 0, 0, 3, and then 3, 2, minus 1, minus 1. Multiplying, we'll get 6, 4, minus 3, minus 3, and then we'll get 6 minus 6 is 0. 4 minus 6 is minus 2. Minus 6 and positive 9 is 3. And negative 4 plus 9 is 5. So we have P inverse dP equals A. The matrix A is diagonalizable. As an example of a matrix that is not diagonalizable, let's suppose A is the matrix 2, 1, 0, 2. Seems simple enough, but turns out this one does not generate an eigenbasis, and hence it is not diagonalizable. You can see lambda equals 2 with algebraic multiplicity equal to 2. It appears twice on the diagonal. That's step 1. Subtract 2 from the diagonal, and you get y is 0 but no constraint on x. The eigenspace will be the set of all t times 1, 0, such that t is an element of the set of real numbers. In other words, a basis for the eigenspace will consist of 1, 0. It has dimension 1, so the geometric multiplicity is 1. Notice that there's only one eigenvalue, but the eigenspace is one-dimensional. You can't generate then a basis for R2 of eigenvectors. The eigenvectors lie in a one-dimensional subspace of R2. That means this matrix is not diagonalizable. I'm going to state a lemma. Eigenvectors from different eigenspaces are linearly independent. if eigenvectors come from different eigenspaces, they have to be pointing in unique and different directions. They can't be linear combinations of the others. Suppose lambda 1 is not lambda 2, and v1 is an element of e lambda 1. v2 is an element of e lambda 2. Then suppose 0 is c1 v1 plus c2 v2. c1 and c2 not 0. What does that mean? If we multiply both sides of this equation by a times 0 is still 0. A times v1 is a v1 and a times v2. But remember that v1 and v2 are eigenvectors corresponding to lambda 1 and lambda 2. We have c1 lambda 1 v1 plus c2 lambda 2 v2. Now, let's multiply this equation through by lambda 2. Let's multiply this equation through by lambda 1. I've stacked these because I intend to subtract these two equations. When we subtract, 0 minus 0 is 0. c1 lambda 1 v1 minus c1 lambda 1 v1 is 0. What's left is c2 lambda 2 v2 minus c2 lambda 1 v2. Now we know that c2 is not 0. And since lambda 1 and lambda 2 are not equal, lambda 2 minus lambda 1 is not 0 either. The zero product theorem says one of these factors is 0 and there's only one left. That means v2 is 0, but wait a minute. v2 is an eigenvector. v2 is not the zero vector. This is a contradiction, which means we've made an assumption that's false. Our assumption was we could have a non-trivial linear combination with v1 and v2 equal to 0. That's only valid if v1 and v2 are linearly dependent. Since that is not the case, we deduce that v1 and v2 are linearly independent. They have to contribute something new in terms of a direction in space. As an immediate corollary, we have the following. If some n by n matrix has n distinct eigenvalues, then A is diagonalizable. Each eigenspace will be one-dimensional and linearly independent, so you will in fact generate an eigenbasis, and that implies diagonalizable. In our next example, I want to show that every real symmetric 2 by 2 matrix is diagonalizable. And to that end, suppose A has the form A, B, B, C. It is symmetric because A transpose equals A. We'll assume that A, B, and C are all real numbers, and this is 2 by 2. Real symmetric 2 by 2 matrix. Let's see what we can find out. First, the characteristic equation. We'll have A minus lambda, B, B, C minus lambda. This gives us A minus lambda times C minus lambda minus B squared. Boiling this out, we have a positive lambda squared. We'll have a negative a and a negative c lambda. Then we have plus ac minus b squared. If we can show that the characteristic equation has two different solutions, then we'll know that the original matrix is diagonalizable. We'll use the quadratic formula. The negative of the middle term, that's a plus c, plus or minus square root b squared, that's a plus c quantity squared, minus 4ac, ac minus b squared, all over 2a. We need to simplify this. We'll have a plus c plus or minus square root. If we FOIL this out, we'll have a squared plus 2ac plus c squared, but we'll have minus 4ac plus 4b squared all over 2. Now, 2ac minus 4ac gives us rather a minus 2ac, and we can factor this again. We'll have a minus c quantity squared plus 4b squared all over 2. Now, provided what's under the radical is not 0, we will have two distinct solutions. If a minus c squared plus 4b squared is not 0, then a has two distinct eigenvalues, and that implies a is diagonalizable. What about the other case? Suppose a minus c squared plus 4b squared is 0. Then what? If a, b, and c are all real, the only way that can happen is if a equals c and b is 0. But if a is equal to c and b is 0, the matrix is already diagonal, implies that it is diagonalizable. And that's it. We have the following theorem. If A and B are similar, then they have the same eigenvalues. Let's prove this. If A and B are similar, then A is P inverse B P for some invertible matrix P. Let's look at the characteristic equation on A. We'll have A minus lambda I. The eigenvalues will solve this equation. Let's look at the characteristic equation with A replaced by P inverse BP. And we're going to switch out with I and replace it with P inverse IP. And that way we can write this as P inverse times B minus lambda I times P. Now remember, if I have the determinant of AB, that's the determinant of A times the determinant of B. Also, the determinant of P inverse is 1 over the determinant of B. So we get 0 equals this first part, but also equal to 1 over the determinant of P times the determinant of B minus lambda I times the determinant of P. And we get the determinant of B minus lambda I still equal to the determinant of A minus lambda I. That means that the eigenvalues of A will solve the same characteristic equation as the eigenvalues of B. That implies B, A, and B, they have the same characteristic equation, and therefore the same eigenvalues. As an immediate corollary, let's suppose that T is a linear operator the dimension of the vector space V is n, and that is finite. And B1 and B2 are bases for the vector space V. Then the coordinate representations of the linear transformation relative to either of these bases, we already know that they are similar. Any coordinate representation with respect to one basis will be similar to the coordinate representation with respect to another basis, and hence these will have the same eigenvalues. We'll state the following theorem without proof, leaving it for an upper division course in linear algebra. A matrix A, that is square, is diagonalizable if and only if characterization for each eigenvalue, the algebraic multiplicity is equal to the geometric multiplicity. So each eigenspace has to have the same dimension as the algebraic multiplicity of the particular eigenvalue.